Good afternoon from China. I'm Renfei Xu from Shanghai PGM Technology, and my topic today is interface protocol design in Capella. And there are four parts in my presentation. The first one is the background, and the second one is the introduction of interface design in Capella. And then I will introduce our extension to do interface protocol design. And the last one is the conclusion. So here comes the first one, the first part. First of all, I would like to introduce my company first. I'm from PGM, and which is short for Pugo Mountain. Pugo Mountain is from Shanhaijing, which is an annal of geography in ancient China. And PGM is now a leading provider of MBSE solution and a consulting service in China. So this is the logo of our company. As for me, I'm Renfei Xu from PGM, and I'm the technical director of MBSE. I have participated in many implementation projects in MBSE in areas like engine control, avionics, mechatronics, and radar, and so on. In recent years, I am dedicated to the promotion of Capella and Arcadia in China. And as the topic is interface design, so I will take some time to discuss the challenge of interface design. We know that in the development of complex systems, interface design is always one of the core tasks. It mainly defines the interface structure, message protocol, and cable connection between various equipment, subsystems, devices, and modules. The traditional way to design interface is based on document, which is interface control document, and it's facing more and more challenges. The first challenge, I think, is that ICD document is hard to support collaboration. We know that interface information is always related to a lot of stakeholders, and each of them has the intention to modify this document. So usually we will need a strict version control of the ICD document. But in the real life, we may find that different stakeholders are reading different version of the ICD document. So that will produce some chaos. So if we are not sharing the same data, the same version, the collaboration will be not very effective. And also inside the ICD document, the information are always interrelated. So when you modify one place, you need to think carefully about how many other places should be also renewed. And considering the large amount of data and also the complex format of different tables. So they all makes the document very hard to maintain and also hard to be reused. And the next challenge is that the rules between different pieces of information inside the interface document is very complex, and that makes it difficult for the computer or the software, the tool, to check, to verify the correctness of the ICD automatically. So it mainly relies on engineers to check the correctness, and it's not so, it will always cost a lot of effort. And as we mentioned version control before, so the version control of ICD information is usually based on the document, the whole document. And it's not easy to control the version of each table or even each cell inside the table. So we think the granularity of data management based on document is too coarse. And another challenge is that the ICD document is usually disconnected with the architecture design document. So when the architecture design is updated, is renewed, we are not sure how many places in the ICD document should be renewed. So there is a gap between these two documents. So the conclusion is traditional ICD need to be improved we should use some more advanced method to design interface. And here is an example of traditional ICD document. So it's a typical table. And for example, we have a payload named request here, and this payload consists of 7 fields. And for example, the first field, it takes 2 bytes to represent 2 characters, and these 2 characters means the PID code. And for this typical table, we usually will have a lot of questions. For example, what is the relationship between this ICD table and the architectural definition diagram, which is usually defined in VSD file or even in PowerPoint slide. So there is no connections. And the second question maybe, is it the same in the document of different modules? So we will have requirement definition document, we will have architecture definition document for the source module and for the targeting module, and they are all related to the interface information. But we're not sure that all these information are consistent. And then the next question may be, who has the authority to modify it, and who has the authority to get the latest version of the table and to use it, and some and other questions like that. So here comes the second part, what we can do in Capella to define interface information. So we will take a quick review of Arcadia here. This is a global view of Arcadia. It contains mainly 4 parts: the operational analysis, system analysis, logical architecture design, and the physical architecture design. And in the first stage, the operational analysis, we will define what the users of the system need to accomplish. And in the system analysis, we need to answer that what the system has to accomplish for the users. And then in the logical architecture design, we will define how the system will work to fulfill expectations. And in the last part, we will define how the system will be developed and built. And in each of these 4 stages, we can define some kind of interface information in different granularities. For example, in the physical architecture, we can have node physical components here, these yellow blocks, and we have behavior physical components here, these blue blocks, and we can define functions here, physical functions here, these green blocks, and we can use functional exchange to define the input and output of the function. And we can use component exchange to define the interface between different behavior physical components. And we have physical link and physical path to define the interface between different node physical components. And in addition, we can also define exchange item for the functional exchange. And even we can define the class properties inside each exchange item. So we can already define a lot of information related to interface in Capella. And in the perspective of interface design, we can take the physical link as the cable connection between different hardwares, and we can take component exchange as the protocol name between different software, and we can take functional exchange as the message between different functions. And the exchange items can be used to represent payload, and the class properties can be used to mean fields. So it's already very powerful to represent the interface design information. but it's not it's still not enough for the interface detailed design. So we have developed an interface extension to do the protocol design. And first of all, we will need to define the bus structure based on our physical architecture. So we have developed a model element called bus network. We can define bus type, basic properties, roles, and addresses for each module. For example, we will have a bus network, and maybe we have 3 modules inside it, and one is master, and the other 2 are slaves, and each of them will have its own address. So these can all be defined by the bus network, and the bus type can support like 1553B, CAN, HDLC, and so on. And inside a bus network, for each functional exchange, we can define its relevant messages. So that there can be one or more messages related to one functional exchange, and these messages can be strongly related to the exchange item or not strongly related. They can be optional. And for each message, we can define its basic properties. For example, the cycle time, the amount of data, and the description. And we can also define its inside structure, including the header, the body, and the trailer. If the message body has more than one payload, we can also define the name, the length, the content, and description of this payload. So these are all extended based on Capella. And what's more, all the message information can be predefined and managed in a database on a server. And users can reference this message information from Capella client. And this can make the information reuse, the message design reuse, and the standardization very easy. And inside the message, we can define several payload. And for each payload in a message, we can also define its basic properties and the meaning of each bit or byte. For example, for this message, we have four payload, and for the last payload, we have 2 fields, and the first field has 64 bit representing one integer, and this integer has a name, has a code, and also you can define a description for it. And the next field is also representing another integer with the different name, different code. And also all the payloads information can be defined and managed in a database or in a library on a server, and which can be referenced from Capella client for quick reuse and standardization. Then let's come to the cable design part. For the physical link and the physical port, they can be used to define the cable connection between different hardwares. And for the physical ports, we can use it to represent physical connectors. And inside it, we can define different pins. We can define pin numbers, the pin number, the pin name, pin type, and the descriptions. And usually for one connector, one physical connector, we will have a lot of pins. So we can define a device library to be referenced. And if you reference a device in the database, then all the predefined pin information will be pulled out and show up in the Capella client. Then for all these pins, if you are using differential signals, we can define differential pairs based on the physical pins. So in this example, the second pin and the third pin are defined as a differential pair. Then we will have a mark here showing that these 2 pins are inside one differential pair. And for a physical link, we will have two physical ports on each side. So if we have defined all the pin information on each physical ports, then for this physical link, we can map these pins automatically based on the name. So if on the one hand we have a pin named signal 1 for in one physical port, and on the other hand we have another physical port containing a pin called signal 1, then in our extension we will map them automatically because they have the same name, and all these names can be predefined in the device library. And for each physical pin or each differential pair, we can allocate one or more messages to them. So in this message allocation wizards, we will show the relevant the relevant messages that can be allocated. So for a physical for a physical functional exchange, we will define several messages, and this physical functional exchange will be allocated to a component exchange, and the component exchange will be allocated to a physical link. Then for this physical link in the message allocation wizard, we will show up the relative messages. Then we can choose which message is allocated to which pin. And if your model is defined completely, then you can highlight the entire message transmission path within your physical architecture model. So for this example, we have a lot of node physical component defined and a lot of physical port, physical link. Then we can for the extension, we can choose to highlight a signal, for example, signal 1. Then all the physical link and port that is related to signal 1 will be highlighted. Then we can check if the entire message transmission path is correct or it's break. Is there any breakpoint? And so we can check it by engineers, or we can check it by the tool by predefined rules. So it will make the interface design more easier, a lot easier. So that's the introduction of our extension. Then the last part is the conclusion. So with our extension, we can get a lot of benefits. So the first one is we can get an integrated design process from architecture design to interface design, because our interface model are right based on the architectural model. They are tightly connected to each other. So if the architecture model is modified, the interface will also be modified related to the architecture. So the design process, the model data, they are all integrated. And the second benefit is effective data control, because the interface information are right inside the architecture model. So when you control the version of the architecture model, it means you also control the design of interface. They are controlled together. And we know that architecture model or system model is more effective in collaboration compared to document. Then the interface information inside the architecture model are also easier to be used in collaboration. So the third benefit is the easier collaboration. And also in the interface model, in our extension, the information are also much fine-grained compared to the ICD document, and we can control a piece of the interface. We can control a message. We can control a payload, a field, and even a pin inside a cable. So it will enable easier collaboration. Then with the predefined rules, we can make the tool verify the correctness of interface design automatically, and we can highlight the message path to help the users to check the result, the design result by human or by tool. They are all very convenient. And the next benefit is the standardization. So using our tool, using the extension, we will have a standard design process. We will have a standard design method, a standard template, and with all the library, we will have standardized data. So it will be easy to use all these model to reuse model to enable future design. And so the last benefit is the efficient data reuse. So with the database of messages, payloads, and devices, all these things can be quick reused. Okay, then let's make a conclusion. So Capella is already a good platform for architecture design. Engineers can use it to define functional exchange, component exchange, physical link, and relative data structures. But it's not enough for interface protocol detailed design. For those who are still using documents to do interface detailed design, or using several separated tools to design protocol and cables, it will be much easier for them to design interface protocol based on architecture model directly. And we have developed this extension on Capella to help us do bus structure definition, message design, signal design, and preliminary cable design. And all this information is tightly connected and is traceable to each other. Okay, that's all for my presentation. Thank you for your attention.
All right, thank you very much for your presentation. So we have a first question from Marek. So is there any method to export the data in tabular, Word, PDF formats? Is the server needed to use this plugin? And if so, what kind of server it is?
Um, because our extension is extended based on the Capella model, so the how do you say, so the word export module for Capella can also be used to export all the interface information. So the M2doc module, the M2doc can also be used to export these things. And also we have other file generation solutions. They can be done. And for the server part, if we want to reuse the message, reuse the payload, reuse the physical connector design, then we will need a server. So the server is also developed by PGM, and we will build a lot of database on it. So if you don't need to reuse this information, you can simply use the extension on the client and with no server.
Okay, thank you. Is it possible to share this Capella extension? And is it easy to maintain this extension with the evolution of Capella version?
This extension is commercial, so we can discuss later if you are willing to buy it or you want to try it, and we will maintain the extension based on different version of Capella. So I think it's not a problem.
What about layered protocols? For example, there is RG45 for L1, the L2 frame with MAC addresses, then L3 frame with IP, etc. Is there a possibility to structure those structures and reuse them across different interfaces?
For the extension now, we are only used to define simple protocols. So if we have protocols with multiple layers, we can make some further extension based on the protocol extension now. So I think we can do it further if we have the requirements.
Can you explain the properties shown on slide 12 and how did you extend the Capella model with this bus component? Is it Java programming required or rather Python scripting?
The it's not clear on the slide. So this is the cycle time. This is the bandwidth, the master module, and the direction of the clock, the direction of the data, something like that. And it's the rate, the communication rate. So and these are the module name, the module type, it's a master or slave, and the address, and something like that. And for the mm, for the code, developing code, it's done by Java.
All right, thank you. Another question about the slide. So another slide, the slide 23. What are those special icons on page 23? Is it male-female connector? So maybe I will let you share your screen on slide 23.
Uh, yeah, you can take it as a male female connector. Yeah, we have extend some extra model elements based on the physical port.
Specifically related to China. So are there many companies using Capella in China? And what are the industries involved? Like, for example, automotive, trains, military, or other?
Uh, yes, there are several companies using this extension in China, and it's mainly in the defense domain.
Okay, so thank you very much, Renfei, for your presentation.